Hello, all you Volkswagen lovers. As I, at least to the people in the particular Facebook group, said I would publish some videos, and here we go. I guess the most important part is about testing it, because I was working on a presentation about how it works, and I'll get there. But at the end of the day, you don't need to know much detail about that to test it. And I'm not going into kind of testing you could do when it's still assembled on the bench. Basically, I don't know, it's a good point, but I don't think that you can do a full-on test of it. Of course, you can bring it into the auto parts store. I'll have to think about that. But anyways, the reason as you know, I'm rebuilding the engine, and one of our colleagues said something funny, a great statement I liked. What is it? The might as wells, right? You got it all apart, so you might as well do this, you might as well do that. And but I actually did have a problem with the alternator, and so this prompted me to take it apart. I could have bought a new one, but and I had nothing to lose in this case. So the bottom line was, and let's find those slides again. Yeah, the bottom line was that when I would measure, if you can see my hand waving there, so I would measure, this terminal goes straight to the battery. Oops. So the B terminal, let's see what we got here, red, good. So that's the B terminal there, huh? So I put my voltmeter there, and I would put the red one there, and then the black one to the negative terminal of the battery, for example, or just to the frame of the car. And of course, you're going to measure the battery voltage. Great. All good. But then, because what was happening is when I was shutting off my bus, I had installed some relays up front, and then also the stereo would make all kinds of it was drive you nuts, noise every time I turned the thing off. So what was happening is that if I took my voltmeter once again, and now I put it on the D plus terminal, so you look at the alternator body here, this is the D plus terminal there. Let's see if I get the light to show the D plus. Well, we know it's there. And I also would measure 12 volts there. Now, right off the bat, I was a little suspicious, but this is when I started digging into how alternators in fact work. And of course, not to you, but it's part of my job as a physics professor. And the whole point of diving into it is because I'm supposed to be a hotshot experimental physicist, and I specialize in hardware design. So this is supposed to be bread and butter for me. So let's think about this now. Key is off, right? So I know I have the battery here. So there's my plus 12 volts. Where can it go? Well, basically, it can't go anywhere because, see, the first place it goes to are these three diodes. And those three diodes are pointed in the other direction. So just to be certain, a diode symbol, so diode is a one-way valve, and direction is always the direction of positive current, even though we sort of know that electrons are really what's flowing, but we don't think of it that way. So if I put positive here and negative here, or at least we have you could have, say, 12 volts and 11 volts. As long as it's more positive here, you get current flow. Now, if you do a reverse bias, so let's say it's 12 volts here and 11 volts here, then current now is going to equal 0. Unless, of course, you overdo it and make too big of a voltage difference here. If you do that, then you release the smoke that everybody knows is inside every electronic device. And if you release the smoke, then you're SOL and you have to buy a new device. Okay. Some part of me wonders if I should be just saving all this, but it's recorded. So anyways, since I read 12 volts there, this is why the stuff in the bus would go nuts, because there would still be a little bit of residual. And I don't have the full story why it wouldn't just leave everything on all the time. The bottom line is I saw that, and what I did is, and you'll see, it's kind of a little tricky to see right here, is that I put a diode inside of a crimp connector, and right there, and then the diode faced, let's see, where's the, right here. So I basically spliced in a diode right here, and everything worked, and it was charging the battery, so that was that, and so good enough. And I didn't have time to take off of work, and I didn't want to, for some reason I had a strong desire to get another Bosch. This is a Bosch, even though I thought originally it was from Germany. It's Brazilian, part of when we restored it, my daughter and I. Since then, I've talked with some local experts here in Southern California, and there's a guy in here in San Gabriel, Eric Beiser, whose dad started the business. He only works on air-cooled Volkswagens and Porsches. And he says he's been using these Chinese alternators, $130, as opposed to, these Bosch's can go up to 200, 250. And even the guys at SoCal Imports in Long Beach, they sell the same one. And they just say we get less returns, right? And Eric and them were talking about the bearings. And I'll go into the rebuild. I went ahead now, because of talking to those people, I went ahead and get Timken bearings. I don't even know if they're made in the U.S. anymore, but they're a U.S. company. And what's the Koyo, right? Koyo is makes bearings for Toyota. I know a lot of people say, "Oh, Koyo crap," but it's hard sometimes to get Timkens for my 72 Scout, so I've been less resistant to Koyo bearings, if you will. So anyways, it worked fine. So now I've stripped down, and one of the parts of the rebuild is that I was reading that you have to go to professionals, because they'll use proprietary hardware, but these are simply Phillips head screws, and that's the pulley end. This is the fan end, and I took pictures of everything, but then since found this diagram, which does before I stopped taking pictures, of course I made sure this matched everything I saw, and it does. And basically the hardest part was that I had to use a puller to get this bearing off at the which end is that? I guess that's this end, yeah, the pulley end. And the fan end, they just slid off by hand. You can see it in the background there, so no big deal. So got that, nice. And so let's take a look at this thing. So once we've got it apart, now this orange line is here because what that represents is everything to the left of the orange line is the voltage, the regulator here. This is a new one I just got. I have the original here, And it's a 3-terminal device, 2 wires, and then the ground right there. So the red is the D plus, the green is the D minus, and then the tab there is the ground. So that thing, I don't have a schematic for it, so I don't know how to test it. And in fact, I have to assume the fault is, well, I assume the fault is there now because I already tested the other diodes. So that's why I didn't order the voltage regulator until I tested the diodes in here. But let's go step by step here. So first, the simple thing, let's take a look at the rotor. And this is where some of the cleverness comes in, and I'll talk about that more and coming up. So the rotor itself is just a single coil inside there, and I didn't want to take any chances of screwing anything up, so I didn't touch that. It didn't need any repairs. So you see there's the single coil, then these 2 metal pieces, and it's really clever because what happens is if you just take any coil of wire and say you put a positive voltage from the battery, you take this to ground, and so if you have a loop of current, so in this case if it was going clockwise around like this, then we'd have the North Pole facing away from us. So let's see if I can do this. So got a loop. Let's say we look. Nah, I'm terrible. That's why I always use diagrams. Anyways, if you say that in this case, you can't tell from the picture. Let's just say it's going around like that, which is counterclockwise. That would mean then that the North Pole is this way. And so, and in fact, I think that, yeah, it matches the diagram on the left. And so you basically just have one coil inside there that say north is one way and south is the other way. And the cleverness is putting these 2 pieces, these steel finger things, because in fact we want the north and the south to point out sideways, because we want it to interact with these coils here. That's number 1. And number 2 is we're getting 6 for the price of 1, because you'll see that there's 1. Oops, let's make sure we get in the camera. 1, 2, 3, 4, 5, 6. So we get 6 norths and 6 souths. And I'll go into the theory in another video. But then instead of having 1 north and south rotating around inside of our outer coils, because the genius here is so now we have 1 rotating coil, but you have 1, instead of having the 1 that you would see here with a north and south and then the 3 outer coils, you get 6 norths and south. So it has, well, I'll explain it another time, but oh yeah, and this is steel, some kind of, it could have some additives to it, but ferrous metals, any magnetic metal acts like a lens, like a light lens. So it brings a north pole, south pole, north pole, south pole. So you get 6 for the price of 1. So instead of having 1 north-south rotation for every rotation of the rotor, you get 6 of them. And where it happened to the slides again? Here we go. And that's the net result. So at the end of the day, the test you want to do here is basically continuity. And I guess we don't need the slides for the moment. So we turn this on, and I'm going to just leave it in home mode. And so we want to see one slip ring goes to one end of the coil, the other slip ring goes to the other end. And there we have it, 3 ohms. I don't actually know the spec, but it seems all right to me. And then just to sort of a double check to get a ballpark idea of it, and this is about the only math we're going to see. So now I've got one of the light bulbs that are used for the oil and the alternator, the idiot lights. And if I measure, one of the things too when you got to be careful not to touch both probes. Yeah, see it reacts. It's mega ohms, but still. But I can touch one as long as I don't touch the other one. And there you go, 8.3. So at least we know this is a good bulb. So so one would say, okay, big whoop. Well, we know we have continuity. Another thing is too, what we can do is we can measure the total resistance, and I'll show you why that is significant in a moment. And since they're in series, well, I would have expected 11.3. It says 11.1. Should be able to just add them together in series. A little more science for you. Well, basic electronics too. All right, we're at 16 minutes. I don't like them to go too long. Slides. All right, so let's take a look. So what happens is, and I have, wait a minute, I have numbers. Here we go. So when you close the ignition switch, and you haven't turned it to start yet, you close the ignition switch. So now the positive voltage is seen here at the D+. It can't go through these diodes, so where else can it go? It can go to the voltage regulator, but it can also go to the rotor. Comes in the D+, and here it is. Comes into the D+, and then one of the brushes is the D+, one of the brushes is the other side, which does go to the voltage regulator, but why is this not working? There we go. So it comes in through, and well, I do know that it goes to ground. I'll have to verify that one. The point is, at that point, it's just a simple circuit from the battery to the light to the rotor to the ground. So that means I got 12 volts and 11.3 ohms. I have 1 amp. And that means that the IR drop, the voltage across the light bulb, is 8.3 volts. And so, of course, let's see, 12 minus 8.3 is 3.7 volts. So what happens is, at this point here, if I put a voltmeter, I'll have to do that when I put it all back together, is 3.7 volts. And apparently, and I didn't wire it up, 8.3 volts is enough for the bulb to light up. And in fact, you may not know this, but when a bulb is on, its resistance actually goes up. So then that would mean that the voltage at the D+ might get closer to 0. That's one of the reasons why Volkswagen probably use the bulb. I don't like it because the bulb burns out and then your charging system isn't working very well anymore. It's also why you can't use LEDs there, because an LED is, and I don't know for sure that the LED is bad. And so there's a little symbol here for the light coming out. And the thing with an LED is that there's a voltage drop across an LED from 0.5 to 0.7 volts. It's called a diode drop. And it doesn't matter what the current is. Whereas with a light bulb, the amount of voltage across it is changing with the amount of current. So then in this case, as once you start the car, the rotor starts rotating and voltage is made. So then you notice that it's delivering it to the battery, but it can also go through these diodes. And this point floats up to 12 volts, hopefully 13 volts. And the light goes out because now, so what would happen? Oh, yes, so then it would be the same. No matter what, if it's, say, 13, it'll be 13 volts at either side. And since there's no voltage difference, there's no current flow, and the light goes out. So then, say the motor starts running very slowly. Also, voltage from the alternator it goes as the RPMs. So the higher the RPM is, the greater the voltage. The lower the RPMs, the less the voltage. That's why you have to have a regulator, because you don't want it to go. You could have it. I was reading that Ford Motor Company had alternators. They used a part of the alternator to produce 120 volts for the front and rear defrosters. Isn't that amazing? And they had to put special wiring harnesses and label them. It's in this PDF I found. It's really useful. So anyways, we got continuity through this guy. At some point, I'm going to replace these brushes because they're very worn out. So I got some new brushes, and that's another video. And so we got that. So that's the easy part.